All right, and still in section 2 of chapter 4, let's see if we can now actually contrast the null space and a column space, right? So that's, we're going to jump into example 5, and the goal is to see if we can contrast these two different spaces. All right, so let me go ahead and read. So example 5 gives us a matrix A. Now, that same matrix A is going to be used for the next couple examples. So I'm going to copy it to each page. But so they give us a matrix A, right, a 3x4 matrix. And what we're asked to do, it says, look, if the column space of A is a subspace of RK, what is K? Right, so the column space of A is going to be in RK space, right? So it could be in two-dimensional space, three-dimensional space, so forth. But the question is, what is K? All right, what space are we in for the column space of A? All right, and then we'll answer the same question, but now we'll be dealing with null space. So let's start with part A. All right. So what is K? K equals what? So let's go, follow me back up here to, let's take a look at matrix A. And I tell you what, let's go ahead, and what I'm going to do right now is I'm going to grab just one column, and I'm going to bring it down here so we can use that one column to answer this question. Ready? So let's assume that I chose the very first column, 2, -2, 3. Now, you will agree with me that that is a column of matrix A. Okay. Now let me ask the question, what space are we in? Well, you got to think of it, there's 3 variables there, right? So we have three different rows, 4 different columns. But look at entries for each row. There's 2, -2, 3. So in this case, K would be 3. 3-dimensional space would be the column space of matrix A. All right, now let's go to part B. So now we're asked to find, so now we're talking about the null space of matrix A. And this is in RK, right, space. And again, we're trying to figure out what dimension of space are we in for when we're talking about the null space. Are we in 3-dimensional space, 4-dimensional space? What are we in? Well, the best way that I can try to explain this to you is so everything dealing with the null space is all about matrix A multiplied by some vector x that gets you to 0, right? That's the null space. So if A is an m by n matrix and you're about to multiply an m by n matrix by some vector, then structurally that vector should be an n by 1 vector, right? So the columns of A have to match the rows of x structurally in order to multiply it. So let's answer this question. So in this case, K would equal what? It would have to equal 4. Does that make sense to you? Does that make sense to you that if you have a 3 by 4 matrix and you want to multiply it by something, right? We want that something to be a vector. Well, whatever it is that you multiply by, it would have to be a 4 by, in this case, 1. So structurally, it would be set up so that we could multiply it. So, okay. So let me go ahead and make the statement that for the most part, your column spaces and your null spaces live in entirely different dimensions. Now, there's a few exceptions, right? If you have a square matrix, or you're dealing with a zero vectors, but structurally, but if you think about it, your column spaces, your null spaces, these are just entirely different dimensions that they live in. Okay. Now, I'm going to come back to, or I should say, this little bit of information here is going to become apparent in the next example. I'm going to read it to you, just so that if I were to forget, I did read it to you, but this will become apparent in just a little bit. So the column space of some matrix A is going to be all of Rm, right? Remember, column spaces are in Rm. But it'll be all of Rm if and only if the equation Ax equals b has a solution for each b. Right? So it will span all of Rm. So let me make sure you understand. Let's come with me back up here to example A. Do you agree with me that since k is equal to 3, the column space is in R3, three-dimensional space? So what I'm trying to say is the column space will be all of R3 as long as there's no inconsistencies in your equation Ax equals b, right? So if there's certain points that you can't reach or not in the domain or that create an inconsistent system, then those wouldn't be in your column space. But other than that, then your column space is going to span all of Rm. Okay, so what am I doing here? So example 6, it says with matrix A used in example 5. So here's matrix A. What we would like to do for example 6 is we want to find a vector, right? Some vector, any vector, just make it a non-zero vector. We want to find a vector that is in the column space. And we want to find a vector that's in the null space. So what's the game? The game is, can you find, we'll call it V, can you find some vector V that's in the column space? And then can you find some vector V that's in the null space? Well, let's start. Column spaces are very easy. Since with the column space, let me grab this picture here and bring it over here. So since the column spaces is just each vector in the column space is just representing the columns of your matrix, then it's very easy for you to find some vector. Let's think about it. Let's just grab one of your columns. So I'm going to grab the very first column of matrix A. Okay, so there's a vector. There is a vector in your column space. Okay, easy. Now let's see if we can find a vector that's in your null space. All right, well, the null space is not as straightforward, okay, because again, we're looking, if you want to find a vector in your column space, just grab a column, easy. But the null space, if you want to find a vector in your null space, it's not as straightforward. What we would have to do is first take your matrix A and then row reduce it, which is what I've done here. Okay, so that's the row reduced. We set it equal to 0, right? So you would set, so since it's AX equals 0, you would set it equal to 0, and then you would RREF your given matrix. Now the question becomes now we're looking at this row reduced form of matrix A, how do we still get to a vector, right? Because I want to say a vector equals something. Okay, well, let's go ahead and move from here back to a system. If that, I'll give you the general solution. So that would be x sub 1 is equal to negative 9 x sub 3. X sub 2 is equal to 5 x sub 3. X sub 3 is a free variable. Hey, what is x sub 4? Is x sub 4 free? No, x sub 4 is defined to be 0. Okay? So it's explicitly defined as 0. So I already know that we're going to have a 0 here. But and again, our goal is to find some vector. So let's think about what would go in I'll go down the row. Let's start with the very first entry, for this vector. So in this case, it would be negative 9, 5. Now, what I'm going to do is, well, actually, let me do this a little bit better. I'm so sorry. My apologies here. So let's assume that x sub 3, since x sub 3 is free, let's assume that you picked 1 for x sub 3. Ready? Now, with this in mind, let's build our vector. So if you choose 1 for x sub 3, we'd have a negative 9 here. If you choose 1 for x sub 3, we would have a 5 here. Obviously, if you chose 1 for x sub 3, we would have a 1 here. And it doesn't matter what we choose for x sub 3 because we would have a 0 here. So there are your two vectors. One is a vector in the column space, and one is a vector in the null space. All right, so again, we're using the same, I believe that we're using the same matrix A. So let me read. So given matrix A that we used previously, they give us a vector u and they give us a vector v. Okay? Our job is to determine if u is in the null space and u is in the column space. All right, let's see if you understand this question. Ready? So we're going to start with just vector u, which is 3, negative 2, negative 1, 0. Ready? Very first question, part A. Is vector u in the null space and column space? Okay, let's start with, is u in the null space? Okay, so that would mean if vector u is in the null space, remember it's ax has to equal 0. So in this case, instead of having a generic vector x, they actually give us a vector u. So this would mean we're trying to figure out if A times U will actually get us to 0. Okay, so this is the question. So all you were going to do is take matrix A, multiply it by this given vector, and see what happens. So I'll do that for you. So if you were to take matrix A and multiply it by vector U, here's what you would get. Zero, -3, 3. Is U in the null space? No. Because it should have, if it's in the null space, then A times U would have equaled 0. Okay, so no, this is not in the null space. All right, what about the column space? All right, well, let me write U. Let's take a look at this vector, and we're trying to figure out if it's actually in the column space. So watch how simple this is. So let me start by asking the question. We're looking just at this vector. This vector is in R what? Is in two-dimensional space, 3, 4. What space are we in? Well, this vector is in R4. Every single vector in the column space, since the column space is always in Rm, and this is an M by N matrix, this is a 3 by 4 matrix, then every vector that is in the column space should be in R3. This vector is not in R3. So no, not in Rm, right? So I don't have to compute anything. This is just no. Okay, so part B, same questions, except now with a new vector. So now they say, they give us vector V is 3, -1, 3. Okay. So let's start with the null space. Okay, so if you want to do, and the null space is, so AX has to equal 0. And in this case, A is a 3 by 4. That would mean that every vector would have to be a 4 by 1. So let me ask the question, is this a 4 by 1? No. So you would need, there's only 3 entries in vector V. So you can't do a 3 by 4 times a 3 by 1. So no, it's not in the null space. All right, what about the column space? Well, this is actually, well, first off, again, look at V. 3, -1, 3. So what space is vector V in? There's 3 entries here, right? So we're in R3. What space is the column space? It's Rm. That's also in R3. So it's possible, right? In part A, we just ruled it out right from the beginning. So this is actually a possibility. But I can make this a lot easier on you. All you're going to have to do is take matrix A with, well, let me go ahead and set it up like this. So I'm going to write AX equals B, whereas this is going to be the B vector. So let me go ahead and write it. So this is A is going to be 2, -2, 3, 4, -5, 7, -2, 7, -8, 1, 3, 6. Now, that's just matrix A. That's just a coefficient matrix. I'm going to go ahead and turn this to an augmented matrix, and I'm going to use this vector V. And here's the deal. All you have to do is row reduce this and see if your matrix is a consistent system. So let me erase because I've ran out of room here. So if you take your AX equals B, in this case, because we're dealing with column spaces, and you're using V, vector V is being plugged in here. You've set up your augmented matrix, and now you grab your calculator and use that row reduction algorithm, and here's what your calculator gives you. Now I can't remember if I RREF'd or REF'd. I can't recall, but let's just assume that this is what your screen looks like. Okay, so yeah, so as I said, I can't remember how I went through and when I started this reduction algorithm, but here's the thing. The only question that you have when you're done reducing is it consistent? So is the new matrix consistent? Right? Do you have any consistency, meaning like an inconsistent system where you would have a bunch of zeros in your and let's say if these were all zeros and this were equal to 1, well then you can't add up a bunch of zeros to get to 1, so that would be an inconsistent system. So in this case, and you can do this on your own, if you row reduce this matrix that I wrote here, the result would still be a consistent system, a consistent matrix, so you can answer yes. It is in column space. All right, so I know that's a lot. We're done. This little page right here does a pretty good job contrasting the null space and the column space for some matrix. So you can, I'll leave this here for just a second. You can read through that. And then on this very last page, I'm just going to show you the geometry of the null space versus the column space. So, okay. So you can see that what they have is, we're thinking about, you know, if you're moving from 2-dimensional space to 3-dimensional space or vice versa, there's some type of transformation that's being undertaken, right? Some linear transformation. And you can, everything that I'm about to say is in this diagram, in this definition that I've put here. All I'll say is just some vocabulary. So sometimes you'll hear the null space of A referred to as the kernel, and sometimes you'll hear the column space of A referred to as the range. But other than that, my voice is starting to go, so I'm going to go ahead and conclude this lesson.